Good day. My name is Chandler Emononget from CM124-1B12 under the supervision of Dr. Catlia de Castro Cruz. And today we're going to be discussing atomic spectroscopy and we will be answering question 28-3. So in question 28-3, why is atomic emission more sensitive to flame instability than atomic absorption? Atomic spectroscopy are used for the qualitative and quantitative determination of more than 70 elements. Typically, these methods can detect parts per million to parts per billion amounts, and in some cases, even smaller concentration. So these methods can be divided into two groups: optical spectrometry and mass spectrometry. So for optical spectrometry, it is the technique of measuring the intensity of absorption or emission of radiation in the ultraviolet visible region of the spectrum. So in analytical application, these measurements are made by exciting in various ways transitions of electrons between outer orbitals of atoms, ions, or molecular species. So in most applications, this is necessary to dissolve the sample before the analysis. So for the mass spectrometry methods are based on forming ions in the gas phase and separating them based on mass to mass charge ratio. So in the mass spectrometry, analyte molecules are converted into ions by applying energy to them. The ions formed are separated on the basis of their mass to charge ratio and directed to transducer that converts the number of ions abundance into an electrical signals. Atomic emission spectrometry. In atomic emission spectrometry, analyte atoms are excited by heat or electrical energy. So the energy is typically supplied by plasma, a flame, a low pressure discharge, or by high powered laser. So before the external energy source is applied, the atoms are usually in the lowest energy or ground state. The applied energy then causes the atom to be momentarily in a higher energy or excited state. A transition to or from the ground state is called resonance transition, and for the resulting spectral line, it is called resonance line. So, atomic emission spectrometry is widely used in elemental analysis, and the ICP is now the most popular source for emission spectrometry, although the DCP and flames are still used in some situations. So, the ICP is widely used in determining trace metals in environmental samples such as drinking water, wastewater, groundwater supplies, and it is also used for determining trace metals in petroleum products, in foodstuffs, and in geological samples. So the ICP has proven specifically useful in industrial quality control, and the DCP has found a significant role in trace metal determination in soil and geological samples. So flame emission is still used in some clinical laboratories determining sodium and potassium. So for the instrumentation of atomic emission spectrometry, so the black diagram here of a typical ICP emission spectrometer is shown in this figure. So atomic or ionic emission from plasma is separated into constituents, wavelength, isolation device, this, and this separation can take place into a monochromator or a polychromator or a spectrograph. So the monochromator isolates one wavelength at a time at a single exit slit, while the polychromator isolates several wavelengths simultaneously at multiple exit slits. So for spectrograph, it provides a large aperture as its output to allow a range of wavelength to exit. So the isolated radiation is then converted into electrical signals by a single transducer. So, or it's either array detector. So the electrical signals is then processed and provided as input in the computer system. So flame emission spectrometer and DCP emission spectrometer follows the same block diagram except that the flame or DCP is substituted um, here in this figure. So mostly flame spectrometer is isolate a single wavelength while DCP's spectrometer may isolate multiple wavelengths with a polychromator. So for wavelength isolation, emission spectrometry is often used for multi-element determination. So there are two types of instruments generally available for this purpose. So the sequential spectrometer uses monochromator and scans the different emission lines in sequence. So usually the wavelength to be used are set by the user in a computer program, and the monochromator rapidly slews from one wavelength to the next. Alternatively, um, monochromators can scan a range of wavelength. So the simultaneous spectrometer uses polychromators or spectrographs. The direct reading spectrometers uses polychromator with as many as 64 detectors located at exit slits in the focal plane. So some spectrometers use spectrographs and one or more array detectors to monitor multiple wavelengths simultaneously, and some can even combine scanning function with spectrographic function to present different wavelength regions than array detector. So the dispersive devices in these spectrometers can be gratings, um, prism combination, and HL ratings. So simultaneous instruments are usually more expensive than sequential system. So for the radiation transducers, single wavelength instruments most often use photon multiplier transducer as a direct reading spectrometer. The charge coupled device, or well known CCD, has now become very popular as an array detector for a simultaneous and some sequential spectrometer. Such devices are available with over 1 million pixels to allow a fairly wide wavelength coverage. So one commercial instrument uses a segmented array charge coupled device detector to allow more than one wavelength region to be monitored simultaneously. For the computer systems and software, so commercial spectrometer are now equipped with powerful computer and software. So most newer emission system can provide software that can assist wavelength selection, calibration, background correction, inter-element correction, spectral deconvolution, and standard addition calibration. Also, quality control charts and report generation. Moving on for the atomic absorption spectroscopy. So, in atomic absorption spectrometry, or AA, the sample is vaporized and the element of interest is atomized at high temperature. So, the element concentration is determined based on the anti-attenuation or absorption by the analyte atoms of a characteristic wavelength emitted from a light source. So, an external source of radiation impinge the analyte vapor. So, the light source is typically a hollow cathode lump containing the element to be measured. So, if the source radiation of the appropriate frequency wavelength, it can be absorbed by the analyte atoms and promote them to excited states. Flame atomic absorption spectroscopy is currently the most widely used of all atomic methods because of its simplicity, effectiveness, and relatively low cost. The technique was introduced in 1955 by Walsh in Australia and by Alchemid in Millets in Holland. So the first commercial atomic absorption spectrometer was introduced in 1959, and use of the technique grew explosively after that. The reason that atomic absorption methods were not widely used until that time because it created by the very narrow widths of atomic absorption lines. For the instrumentation, so radiation from a line source is focused on the atomic vapor or in a flame or electrothermal atomizer. So from line source going to the electrothermal atomizer. So the attenuated source radiation is then enters the monochromator that isolates the line of interest. So next would be the radiant from the power source attenuated by the absorption is converted into electrical signals by the photomultiplier tube or the PMT. And then it will be transferred into the signal processor where it will be processed and directed into the computer system. So for the atomic absorption spectrometry, line source is the most useful radiation source for atomic absorption spectroscopy is the hollow cathode lump. This thing, wherein it consists of tungsten anode and a cylindrical cathode sealed in a glass tube containing an inert gas such as argon at a pressure of 1 to 5 torr. So the cathode either is fabricated from the analyte metal or else serve as a support for a coating of that metal. So for this sputtering, it is a process in which atoms or ions are ejected from the surface by beam charged particles. So some of these sputtered metal atoms are in an excited state and emit their characteristic wavelengths as they return to the ground state. So electrodeless discharge lamps are useful sources of atomic line spectra. These lamps are often 1 to 2 orders of magnitude more intense than their hollow cathode counterparts. So a typical electrodeless discharge lamp is constructed from a sealed quartz tube containing an inert gas such as argon at a pressure of a few torr and a small quantity of the analyte metal or its salt. So the lamp contains no electrode, but instead it is energized by an intense field of radio frequency or microwave radiation. So for the answer on the question 28-3, why is atomic emission more sensitive to flame instability than atomic absorption? The answer is because the analytical signal for atomic emission is produced the relatively small number of excited atoms or ions, while in atomic absorption, the signal results from absorption by the much larger number of unexcited species. So any small change in the flame condition dramatically influences the number of excited species. Whereas such changes have a much smaller effect on the number of unexcited species. So the reference as follows. Thank you for listening and God bless.